Hello, and welcome to the last installment of our oceanography lecture series. It is my hope that you found this informative, enjoyable, and I wish you all of the success in your future educational and career endeavors. Today we're going to look at humans' influence on the ocean through environmental concerns and the natural resources that are present in the ocean for our utilization. We'll start off with environmental concerns. This image always reminds me of Finding Nemo. All drains lead to the sea. If you remember, the dentist said that. I believe it was the dentist, but it's true. This storm sewer obviously leads right to the bay, right to the sea, all through St. Petersburg and Safety Harbor and our coastal communities. We see these storm drains, and they also have this stamped on them as well. So wastewater runoff is generally collected wherever you are, inland or coastal, and it is funneled into the local wetlands in the environment. In our case, it's the bay. So this is a concern. Pollution from land actually is land-based sources is the number one mode of pollution in the ocean. So as I mentioned, runoff and discharge 44%, airborne from land 33%. So if you look at direct pollution from the ocean itself, shipping, spills, dumping, and mining, very small percentage when compared to land-based activities. When you look at what a pollutant is, the amount is important, toxicity, and persistence. Persistence is often forgot. Persistence is how long it stays dangerous. If you're using a herbicide and that herbicide only works for, say it has a half-life of a few days, when it rains and there's runoff, it's not going to be as dangerous as, say, using an herbicide or an insecticide with a half-life of years. When you have a long half-life, persistence, a long half-life, how long it's dangerous, half-life, it can move through the food chain and is often amplified. So persistence is very important when you classify pollutants. We'll start off with oil spills. They're the big news. The image here is from a satellite image of the Gulf Horizon disaster in 2010. When you look at oil spills, the amount of oil, obviously, the characteristics of the oil itself. If you spill refined oil, it's more dangerous than if you spill crude oil, and there's actually different types of crude oil as well. The distribution of the oil, where it's spilled, is very important. If it's spilled in an area with a lot of currents, that oil is dispersed a lot greater. If it's spilled in an area near estuaries, estuaries, if you recall, up to 75–80% of sea life uses estuaries for reproduction. The impact would be a lot greater than if it's spilled near a beach. Now, we love our beaches, but an oil spill on a beach means you can scrape up the sand and re-nourish it. An oil spill in an estuary, it really, you can't cut down all the trees in a mangrove forest and expect it to be a mangrove forest. So the distribution of this oil, the location of the spill, it has a great deal of impact on how bad the spill is going to be. So how much? How much per year? You can see the data there. We've been getting better. We've been actually getting better. The quantity of the oil spilled in the 70s was greater than the 80s. And you can see in the 2000s, very little oil is spilled when you look at comparatively. So the annual amount of oil spills has been less. Spills make up only 10% of oil input into the ocean. marinas, leakages, things like that contribute 90% of the oil in the oceans. So crude oil, as I mentioned, is larger in volume because it's and because it's pumped directly from there. But refined oil can be more disruptive because it has been separated into its constituents. It's had preservatives and other things added to it, so it can be more deadly because of the refining process. What happens to oil after it's spilled? The first thing that happens is the volatiles in this oil, the dissolved gases, because it's under pressure in the ground, it's brought up, and hydrocarbons are very volatile. They evaporate easily. So the area around an oil spill becomes very dangerous for breathing, for air breathing organisms because of this evaporation. This evaporation makes the oil heavier. Uh, Light can also degrade it, called photooxidation, reaction with oxygen and light. Eventually, the oils become tar balls and will sink, but that takes a great deal of time. You can see the image there shows you evaporation, photooxidation, oil slick on the surface. Eventually, tar balls can fall out of it and become part of the sediments. Some of it will dissolve. Parts of the oil will dissolve. Oil and water don't mix, but parts of it will dissolve eventually. But the bulk of it can become tar balls toward the end of the cycle. What changes oil chemistry? Evaporation, number one. Those volatiles leave. Oxidation, number two. Produce photooxidation. Uh, some of the compounds are water soluble, and then you have dissolution. So that further changes it. Biodegradation, some microorganisms feed on oil. And emulsification, eventually some of it, oil droplets mix in with the water. So these are processes that affect oil spills. So what do? You see this image is from the Exxon Valdez disaster in the 70s. You can see right on it, they're scouring the beach, trying to wash the oil off, and you can see those booms behind in the background containing the emulsification, containing that floating oil. Those booms, I was surprised. During the Gulf Horizon accident, I was deployed by our local environmental agencies because I had a boat, and I was trained on how to deploy the boom. If the threat was coming towards Tampa Bay, which it didn't, fortunately, I was very surprised that the booms only go down about 6 to 8 inches deep, and then they have the float. So they're not foolproof, but they help to contain the oil slick on the surface. And there they are, booms. You can see those birds are sitting on the boom, perched up, but they're floating skirts, and they contain the oil slick, the part on top. They're not deep, though. And of course, storms can wash over them. So they're a quick response to try to contain and funnel that oil toward less environmentally sensitive areas. Slick liquors are areas are like huge paper towels to pick up the slicks. It's not you're not going to be able to slick lick up entire oil spills, but in areas that are super environmentally sensitive, they can help control the spread. Uh, Dispersants have been used in the past. They generally are highly toxic, so you have to consider it the lesser of two evils because you're adding chemicals to a chemical spill, if you will, and they are to disperse the oil, break it down more quickly, but they don't necessarily clean anything up. Controlled burns, air pollution. Uh, the black plume of smoke puts soot and particulates in the air. But again, it helps if that oil is in a current moving toward environmentally sensitive or a populated area and causes a greater concern. So it's the lesser of two evils again. Of course, cleanup is very expensive. There's the Exxon Valdez disaster again in Alaska, and they have rocky beaches in Alaska, and they are spraying those rocks with high pressure to try to clear the surfaces. Dispersants are also used, and bulldozers scraping off the upper layer of beaches. Beaches are easier to clean up than environmentally sensitive ecosystems. So one response is to try to funnel the slicks toward beaches. So we'll look at case study, the Deepwater Horizon accident. Uh, April 20th, the Deepwater exploded, and there was petroleum. BP was in charge of it. It was in American waters, but BP had an arrangement to harvest the oil. 11 workers were killed. Up to 1.7 million gallons a day were spilling into the Gulf. So it was the largest disaster oil spill in American history. They tried to dig a relief well to divert and pump oil to lessen the amount that was spilling. U.S. regulations were a little more lax when it comes to relief wells. Another is the Exxon Valdez, 1989, Prince William Sound. This was the largest tanker disaster. The captain ran aground in Bly Reef. Uh, it had a devastating effect on the wildlife in this Prince William Sound, in the Aleutians in Alaska. The economic impact at the time was $2.1 billion spent. Now, that was an astronomical number for when this occurred. Also, almost 1,500 miles of coastline was affected in Alaska, the Aleutians. The Aleutians are a chain of volcanic islands off of Alaska. The second type of pollutant I'd like to talk about is toxic waste. Okay, so we're off of oil onto toxic waste. DDT, great wrestling move by Jake the Snake for old people like me. Uh, but DDT is a pesticide commonly used in the late 60s. What happens is it has a long half-life and moves through the food chain. So when it reached the top of the food chain, large birds, the eggshells became thin and disrupted the reproductive process. It was also found in human breast milk, by the way, not as public as the bald eagles, America's symbol, that were becoming endangered because of that. Now, the interesting thing about DDT and the bald eagle is our response to it. We got the good and the bad. Our good response was laws started, and actually the EPA was founded because of that. The Endangered Species Act was passed. DDT was banned for use in America, and it really started the ball rolling as far as environmental protection by the federal government. So that's the plus. DDT was still being produced and sold to other countries. there's a minus. But DDT and the bald eagles really got the ball rolling for the EPA and the federal government involved in environmental initiatives. DDT and other pesticides show biological magnification. Notice trace amounts in the water, but as it moves up through the food chain, it becomes more and more concentrated. That is what biomagnification means, and that is why persistence is so important. Pesticides are chosen because they break down quickly. You never make it to the top of the food chain where it's highly concentrated. All right, so as you can see in this image, chemicals are persistent all over, all over. Shellfish and PCBs and toxic chemicals found in our fish livers are on every coast in the Americas. Heavy metals. Now, I'm not a heavy metal fan. I think metallic is okay, but heavy metals in general, another bad joke, by the way. Heavy metals in general cause damage to internal organs, the nervous system, lead, mercury, copper. These were used extensively in industry until lately, where we've cut back on them. They're very persistent. So a lot of places you still can't eat the fish because they have heavy metals in them. The concentration builds up. Oh, if you eat fish and eat fish, and then you start feeling the effects. When I was a college student, I loved to fish, and we used to salmon fish. And the New York DEC, Department of Environmental Conservation, recommended that you don't eat any more than a quarter-pound of fish per month as far as the salmon caught in the salmon river because of heavy metals. They build up in our bodies and biomagnification. So heavy metals are still a problem from our past behaviors. We're working hard on eliminating the use of lead, mercury, and copper. Lead causes damage to the nervous system. Copper causes anemia, liver, kidney damage, stomach and intestinal irritation. And mercury damages the brain and central nervous system, psychological changes. You know the story of the Mad Hatter and Alice in Wonderland? That was mercury poisoning because mercury was used in the processing of leather and the making of hats. Radioactive waste? Well, ever since World War II and Oppenheimer, we've had radioactive problems. You got to take the good with the bad, the lesser of two evils. Nuclear power produces very little waste, but that waste is very dangerous. It has a long half-life, thousands of years, but it produces large amounts of energy without the acid rain, without a lot of the air pollution. So again, I'm not speaking for or against a type of power, but radioactive waste is a problem. Eutrophication is nutrient pollution. The nutrients cause explosive algal growth. The algae dies. Bacteria of decay makes the water hypoxic, no oxygen, dead zones form. Our coastal communities, drainage basins, are very eutrophic due to fertilizer used on crops for agriculture and on lawns for vanity. We have dead zones all over the world, hypoxic areas. So the largest dead zone covers 70,000 square miles. So those are huge dead zones. The United Nations have reported 146 dead zones in our oceans. The Gulf has the second largest dead zone, the Baltic Sea the first. Now, dead zones can recover. Dead zones can recover. When communism fell in Russia, the farmers couldn't afford fertilizer, and those dead zones recovered, proving that nature will heal itself to a degree. Climate change can also lead to dead zones. We talked about El Nino and how that cold water holds more nutrients. Well, warm water is causing coral bleaching and causing areas of explosive blooms, so you have oxygen depleted water. So this image shows coastal dead zones all around major drainage basins. I mentioned dead zones are reversible. I talked about that with the Soviet Union. The Black Sea is the area that was case studied. Sewage. Sewage leads to eutrophication because sewage is rich in nitrogen, phosphorus wastes. California and Mexico there's disputing because obviously different countries have different ways of handling their effluent, and depending on the tides and the currents, Mexican sewage hits the California beaches, and there's a dispute over how to handle sewage treatment. So your treatment plant always has to release water and sludge, wastewater and sludge. So up current is generally negatively affected. We use, I mean, there's no magic water fairy. Sewage treatment. Primary treatment is straining. Secondary, after that, you biologically treat it, allow bacteria to take out the nitrates, phosphates. In some cases, they ozonate it or bubble it, test it, and then release it. Release it into wetlands, further, pardon me, bioremediates. But their sewage treatment is always a concern. Solid waste. This could be our legacy. Plastics. Plastics don't biodegrade on a timely fashion. We have huge garbage patches in each of the ocean's gyres. Thermal pollution, you don't really think of heat as pollution, but boiling water, turn the turbines, produce electricity, have to cool those towers. Whether you're using fossil fuels, nuclear, you're still turning turbines with heat, and you need to cool it so water is pumped in and then warmer water is pumped out. So thermal pollution is something that needs to be accounted for. Speaking of pollution, and we did mention climate change, Earth's temperature is rising. You can see from the image, visible light enters the atmosphere. It's got a little shorter wavelength, a little higher frequency. Earth warms up, and then longer wavelength infrared light escapes out to space, cooling the Earth. And that's the natural cycle. Insolation comes in, and then heat is re-radiated. Now, greenhouse gases from fossil fuel consumption, deforestation, agriculture, block the escaping IR, causing temperature to raise. So oxides like carbon dioxide is number one, but you also have methane, you have other oxides, water vapor, pollutants, soot, airborne pollutants, all help trap heat. So that is what is called the greenhouse effect, rising temperatures on our planet. So global warming is the buzzword used for climate change because we are heating up. Climates have natural swings, so the debate is how much is human, how much is natural. We do know carbon dioxide is rising and has been rising since the Industrial Revolution. Temperatures rising, oceans are acidifying. We know that major mass extinction events in our past have coincided with huge carbon dioxide spikes, either from increased volcanism or some other source. And we could be leading towards a mass extinction, human accelerated. Of course, we're looking at projections, extrapolating data. So the main cause of our greenhouse gases are fossil fuel, carbon dioxide, methane, nitrous oxide, and now deforestation that pulls carbon dioxide out of the atmosphere. When you cut down the forest, you don't have all that vegetation removing carbon dioxide. So these are all contributing to human accelerated climate change. Notice the climate trends. We are warming. Most of that, our current spike, that is, can be traced to the Industrial Revolution. Again, climate change has natural swings to it, but there's no denying we're playing a significant role. Earth's sea level is rising because of the ice caps melting. Our ice caps are thinning, and future coastlines may look more like this than they do today. They have looked like this in the past because we go through these swings, and the Florida platform has been 2/3 larger. There's no denying that these changes will happen with or without humans. There's also no denying that humans are speeding things up. Notice this population curve. Most organisms undergo a similar population curve. They have that lag phase and then exponential growth. You can see exponential growth started to occur around the beginning of the industrial scientific revolution. You can see our first population spike, domestication of plants and animals toward the end of the last ice age, and then agricultural agrarian societies. You can see a little dip because of the plague, but now industrial revolution, biomedical revolution, exponential growth. And our doubling time, the time it takes for populations to double, have been decreasing and decreasing. So we're growing. Oh, this. I watched a lot of this on the Discovery Channel. When they were hunting for crabs. I remember when I was in high school, I liked to fish, and the thought of fast money and a life on the sea was intriguing. So me and my pal, we skipped school one day. Don't do it. This was a past mistake. But and we made plans to graduate high school and move to Alaska and become crab fishermen. Of course, this was just when cable TV came out, so there was no Discovery Channel. I had never watched The Deadliest Catch. I physically would have died because it is rough and it is a lot of work and it is not as fun as going out and catching a few bass or trout and calling it a day. But this is fast money. Notice it's in cold climate because nutrient rich, oxygen rich water, huge amounts of life. But Food is only one of the resources of the sea, and I tell this entertaining story just as a lead into our final topic, marine resources. The international law of the sea, and we talked about the economic zone, that 200 nautical miles out, meaning that the United States controls the economic resources for nearly 10.5 square kilometers. So here's our economic zone, 200 nautical miles, and our territories like Midway or Guam, also we control the natural resources. So in red is the American, United States, we control the resources found in all that area. We classify renewable versus non-renewable resources. Renewable replenish in a lifetime. We can turn a renewable into a non-renewable by depleting it. We can't really do a good job of turning non-renewable back to renewable. In rare occasion, through management, species can recover. Physical resources like minerals, petroleum, fresh water, okay, those are all physical resources. The principal physical resources, salt, potassiums and magnesiums, building materials, sand, gravel, limestone, gypsum. These sediments, manganese nodules, we discussed them before, phosphorites, placer deposits are from erosion, and then ocean rift zones contain a lot of metals from the mantle upwelling. Here's gypsum. Gypsum is a mineral, an evaporite. We use it in plaster. This is Nova Scotia, Canada, and all those cliffs are made of gypsum. Here in Florida, we do have gypsum mines, evaporites. Placer deposits, again, are areas that have deposition from land-based erosion, and we can mine small amounts of gold, silver, tin, chromium, titanium out of these areas, placer deposits. Energy comes from a variety of sources in the ocean. Here's our oil and gas reserves in America. Notice the Gulf Coast is rich in petroleum deposits. We went through oil chains, but what do we use oil for? We went through oil spills. What do we use oil for? You can see we use it for natural gas. Those are those short chain alkanes like propane, diesel fuel, oils, gas, jet fuels, kerosene, plastics, nylon, polyester, lubricants like petroleum jelly, waxes, asphalt. All that is extracted from oil. Oil is mainly carbon and hydrogen. There's other elements in it. It builds up in shallow seas that have been covered by sediment. So sedimentation. Those oil traps have a non-porous rock on top. Those organic molecules separate out. Oils are heavier, gases sit on top of the oils. You can see the anticlines. Anticline is a geologic term for, but if you picture ravioli, the anticlines are the humps and synclines are the dips. So you can see where the gas and oil is, that's an anticline. And then the syncline is right there where there's no gas and oil, and then another anticline. So the oil builds up in anticlines in warped sedimentary rock. We can utilize in the ocean offshore drilling, and that accounts for about a quarter of our oil and gas supplies. The different types of oils, volatile, have a lot of gases, all the way to the tar balls, sinking oils. And these crude oils are you can find oil in any of these stages. An oil spill generally goes from A to E over time. When we talked about oil spills about 20 minutes ago, we talked about the volatiles escaping, photooxidation, all that. About half of our oil, and when they say a gallon, it's 42, or when they say a barrel, it's 42 gallons. About half of that barrel is used for gasoline, and then you can see the breakdown for the others. Refinement is separating these into their constituents. So that's crude oil, and then refined oil has been treated. Another, methane hydrates, is those hydrocarbons that are under pressure, cool temperatures, and they can be mined as well. Solar and wind energy takes a lot of space. It's dangerous for birds, but there's areas with consistent wind that electricity can be harvested from that wind by turning turbines. The turbines, spinning magnets, force electrons to move through coiled wire, and that's energy production. We burn fossil fuels and use this heat to make steam to turn these turbines. We use nuclear power to turn these turbines. And we can use wind, we can use tides, we can use waterfalls, but these turbines need to move. Here's a tidal turbine. Not many locations have good enough tides to produce economically feasible energy, but in some rare occasions, tides can turn turbines. Waves, again, some rare places, waves can produce energy. It can be harvested. Thermal gradients can also be used, but you need to pump water against that gradient, so you use energy to make energy. It's not as efficient. Other things, other resources of the sea, we call them non-extractive. You don't have to remove something. So shipping, non-extractive. Recreation, non-extractive. Unfortunately, waste disposal, which we've already discussed, not extractive. Look at this image. This is an Asian beach. So this causes a great environmental impact, no doubt. Fresh water can be liberated from salt water. Takes a lot of energy to do so, but oceans contain 90% of all, 97% of all water on Earth. We cannot drink salt water because of that salt gradient. We are not equipped to deal with removal of salt to that extent. So a person stranded at sea will die of dehydration by drinking salt water. Some of the biological resources that we pull off: food, fish, crustaceans, and mollusks. You can see that China accounts for the highest amount of fish harvested. The United States is in third place for amount harvested. That Peruvian anchovy industry that we discussed over El Nino, during the El Nino La Nina, that's the second most productive area in the world, is that Peru upwelling. Harvesting farmed plants or animals in the waters called aquaculture, and it accounts for a great deal of our seafood. Multi-trophic aquaculture means you use a lot of different organisms in congruence to, they can kind of, one makes one eats the plankton, and then there's another that eats the feces produced by the one that makes the plankton, and you're using a lot of different levels to produce many different food. One of the tilapia is a big multi-trophic aquaculture because tilapia loves stagnant water and eats the waste. So tilapia ponds are common waste removal ponds, and then that tilapia is sold as food, as well as what you're raising, be it salmon or shrimp, prawn, whatever. Mariculture is a specialized branch of aquaculture using natural methods. In case of this, this is an Asian shrimp farm. Look at all the mountains. This is very susceptible to a tsunami or a flood now, and because those mountains mean there's deep water, it's a active margin. So a lot of tsunamis roll in. If there's mangroves or vegetation there, it beats the wave down. But if you cut open that area and use it for aquaculture, you're getting large amounts of food. But then when there's a flood or a storm surge or, heavens forbid, a tsunami, the impact is far greater. Here's mariculture in a pen. The tides roll in and out, moving plankton nutrients throughout. Very little human interaction, and that's mariculture. It's using the natural environment to handle your aquaculture. Now, commercial fishing, trawling, long lining, and gill nets are the three different methods of commercial fishing. Almost 2 trillion fish worldwide are harvested yearly. There's a shrimp trawler. You can see the size of the net. The problem with our shrimp trawlers is look at that bottom. It's scraping the bottom as well. So you're hurting the benthic organisms, and it's indiscriminate catching. Long lines, indiscriminate killing. You can see random fish hooks are set out with bait, and whatever you get is what you get. A bycatch is something you're not trying to get. Generally, it's just returned to the sea. And gill netting is another indiscriminate catcher. Most, I can't say all, because stone crabs are not over harvested. Most of our fish are over harvested because you're passing the maximum sustained yield. Commercial extinction is when populations are no longer viable to support a profitable industry. Here, Monterey Bay Aquarium, you can see the website. Here's a picture from it. And that is regional. It tells you all the different areas. So if you're traveling, you can get a different area. What choices give you the least amount of environmental impact versus don't eat them, avoid them because they're harvested in a non-ethical or harmful to the population way. Whaling, they still have TV shows about whaling because some countries call it research and still whale. But whaling drove our great whales on the brink of extinction. You can see right there's a large minke whale. They are harpooned and then brought up. That's the second smallest baleen whale, by the way. So there's two types of whales, the toothed whales. Sperm whales are the only great toothed whale. Smaller toothed whales, the orcas, the dolphins, things like that. And then you have the baleen whales. They filter, bulk feed the krill, small fish, things like that, because they don't have teeth. They have baleen strainers. So the great whales, the blue whale is the largest of the great whales. The great whales eat plankton. You can see the fin whale was harvested to the closest to extinction. But during the peak of whaling, you can see how many whales were killed yearly. Over 30,000 fin whales per year. Some real-life case studies of environmental impact. This one was a success story. The Dolphin saved tuna. I do remember tuna boycotts when people were outraged that dolphins were used to find tuna, and then everything was netted, and thousands upon thousands of dolphins were slaughtered in the tuna fisheries. The solution was to promote dolphin safe tuna, and you can see the dolphin safe insignia on tuna cans in your grocery store today. This is one of the rare occasions that consumer boycott actually worked. Shark finning is a terrible thing that is driving many of our shark species to endangerment. The shark fin soup is a delicacy that people eat. The sharks are caught, fins are cut off, and they're tossed back to the ocean. Now, our coral reefs, I did mention how global warming causing temperature rise is causing coral bleaching, which is true, and people are trying to replant, and it's not really plant because they're animals, but replant coral in the Caribbean areas to restore bleached ecosystems. The jury's out on how well it's working, but Caribbean coral reefs, which are called the rainforests of the sea, the Caribbean tract is the third largest reef tract in the world. People are trying to replenish the coral that has been lost due to bleaching. Well, we're at the end of our lesson, the end of the class. Thank you so much. I hope that you enjoyed our lecture series. I hope that this helps you have a greater understanding of our planet. Remember, the oceans are 2/3 of our planet. Thank you for joining us. Have a great day and good luck with your future.